Welcome to the second week of the problem solving session for the course Nature and Properties of Materials, an introductory course. So, week 2 assignment was given to you, and it was all based on crystal symmetry, the Bravais lattices, and it was all basic. So, to start off with, Bravais lattices crystal symmetry, how it's correlated with the Bravais lattice, and how you can form the Bravais lattice, that or not all types of Bravais lattices are allowed. So all these sorts of things were talked about in this week's lecture, and the set of lectures ended with the Miller indices and the crystal planes. Uh, so let us just pop into the assignment section. So yeah, let me share my screen first. So you can see my entire screen, right? Yeah, thank you. So let's just move on to the assignments. And let me just tell you that if you have any sorts of question with the problems that I will be solving, and any question in general regarding the lectures, you can always ask. Just interrupt and ask. There's no problem in interrupting in between. So you have all the liberty to ask your questions. All right. So that is that. So the first question that was asked is shape of the primitive cell of FCC lattice. All right. So the FCC lattice that we have is like this only. So let me just go on to a picture that. So this is your FCC lattice, right? So the atoms are sitting at the corners, and also a simple cubic it's asked, and the atoms are also sitting at the 6 faces. All right. So based on that, you're asked, but considering that 8 atoms are sitting at the corner, so 1 by 8 times 8 plus, and all the 6 faces, they are, just a second. Yeah, so the contributions are in that 8 atoms are sitting at the 8 corners, so, and they are edge shared, so they are shared between 8 cubes, so 1 by 8 times 8 plus, and also the atoms are also sitting at the faces, so half times 6, that gives you a total of 4 atoms. You can imagine that this FCC lattice, this is your FCC lattice, this is your FCC, meaning face centered cubic. So it has 4 atoms, and this can't be a primitive unit cell. All right. So this is a non-primitive unit cell. But the catch is that if you somehow define a new set of for your lattice vectors, which is a function of the original lattice vectors, that is your, as for cubic, all the sides are same. So if it's function of a, which is the side of the length of the side of the cube, so that in that way you can construct a primitive unit cell out of a non-primitive unit cell. All right. So this is how, if you define it, so your A1, which is this, so let me just point out, so A1 is this, so A1 is A by 2 y cap plus z cap, and this is your coordinate axis, this is your x, this is your y, and this is your z. So A1 is defined by the fact that it is half of a in y direction along this direction, and half of a in z direction. So this is your A1. All right. And similarly, like A2 is symmetric, so A by 2 is half of A in x cap direction and half of A in z cap direction. So this is this. Alright, so this is your A2. And A3 similarly, half of A in x cap direction along this direction and half of A in this direction. So this is it. So A1 is half of A by 2 y cap plus z cap, A2 is A by 2 z cap plus x cap, and A3 is A by 2 x cap plus y cap. So whenever you define this set of lattice translational vectors, and if you construct a unit cell out of it, you'll find that this transforms into this. All right. So why did you at first place choose this? Why you chose this lattice translation vectors? Because if you choose this as the origin, what you get is that you get the nearest face-centered atoms. All right. So this is one face, this is another face, and this is another face of the atoms that you get, and you get the nearest atoms. All right. So by that prescription, you can construct using these lattice translational vectors. By this prescription, what you get is this cubic, this unit cell inside the FCC non-primitive unit cell, and this is a primitive unit cell. All right. So this one is your primitive. All right. So it looks like a paralleloparallel. All right. So the primitive unit cell for a face-centered cubic cell is like a paralleloparallel. So this is somewhat you can understand. So the first question would be, the answer to the first question would be, the shape of the primitive cell of FCC lattice is like a paralleloparallel. All right. So the correct answer is paralleloparallel. And you must have noticed from the lectures, if you have followed the lectures well, Professor Garg told you about this. So you must have noticed this. All right. So let's move on to the second question. The symmetry operation or operations present in a 2D crystal lattice are. So as you can understand, it can be a multiple answer question. So the inversion symmetry, let's just start with the inversion symmetry, what it's like. Let's say there's a simple cubic, your structure. Sorry. So this is your simple cubic structure. What you get is this, right? So that's that. So this is it. Now if you draw a diagonal, so this is two joining two vertices diagonally. This is your diagonal, and this is your center of inversion. So inversion basically means is that, so if this point is marked by A and this is marked by B, so inversion basically means, and if this is your coordinate axis, and if this is your coordinate axis, this is your Z, this is your Y, and this is your X. All right. So what it basically means is inversion operation means that X, Y, and Z transforms into, under inversion, transforms into minus X, minus Y, and minus Z. All right. So if this is your inversion center, what you have to basically do under this transformation is that A goes to B and B goes to A, if this is your 2 points. So what we have to do is this inversion along with rotation, you also have to do a mirror symmetry. So for a 2D crystal, as you might notice, So this is your 2D lattice, as you have already seen from the lectures. So now if I draw what the options are given, that it's inversion, reflection, rotation, and screw. All right. So so if you consider this simple case, where it is the simplest, where A equals B and theta equals 90 degree, you can always have a mirror plane, right? So if you draw a mirror axis or mirror plane along this, so both two sides are mirror images of each other and they are symmetric. All right. So you can have mirror symmetry. You can have mirror symmetry, which is reflection or reflection. All right. Now, if you think about a unit cell, this is a four-fold rotational symmetry. All right. Now, if you along this axis, if you rotate, so if you rotate by 90 degree, it will always be the same. So that's why a four-fold symmetry. And along this directions, along these points, these are twofold. Of course, for fourfold you can always have a twofold symmetry, but along these lines also you can always have this. Sorry, this twofold symmetry, and these are rotational symmetries. Okay, plus rotation symmetry. Why you cannot have a inversion symmetry is just because of the fact that inversion involves a rotation and a mirror image of those things. It always, just a second, someone, yeah. Is there a problem with my screen sharing? My screen is visible, or when I was calculating, my screen was visible, or was it visible, right? It was visible, right? Yeah. Oh, sure. Thanks. So, where were we? So, so for rotation, for inversion symmetry, you have to accompany a reflection and a mirror reflection. So it will be on the plane out of this 2D lattice. So you have no liberty to go in the z direction, right? So for this, of course you can have symmetry, like this is your, of course, if you rotate, like if you rotate by 180 degree, this sphere will go to this. All right. And if this is your origin of inversion, you can always have a inversion in the 2D lattice. But the convention is such that you have to have a rotation and a reflection along with it. So you have to have a rotation in the 3D lattice, 3D direction, that is the z direction. And that's why we tell that the inversion symmetry is present only for 3D lattice. So by convention, what we have, yeah, the answer to that will be that reflection is possible. All right, as we saw that the mirror, we can put a mirror plane and we can have a reflection of the other part. So reflection is possible, and a rotation, screw, and inversion, these are not possible for 2D crystal lattice, right? Because as I said, in inversion you have to have a rotation in the third direction, that is a z direction. If you consider 2D lattice, the z direction has to have a rotation. So in that case, 2D lattice cannot have that freedom to rotate in the z direction. So the inversion symmetry is cancelled out for 2D lattice and it goes out of the equation. Right? That's true, as you can understand, it's not even possible for 2D lattice. So we are done with two questions, and the number of primitive lattices in a BCC lattice. So this is directly from the lecture, and what you can see is that this is your BCC unit cell. All right. So 4 atoms are there at the two. So 8 atoms are there at the 8 corners, and there's one atom at the center of it. Just let me check. Yeah. Yes. Those just yeah. So what it basically means that there is one atom at the center and 8 atoms at the corners. So how many atoms are there? So effective number of atoms are 1 by 8 times 8, because the corner atoms are shared by 8 such cubes. All right, plus 1, and that is 2. All right. So now they are non-primitive unit cells. As you can imagine that this, it's not one atom per unit cell, it's 2 atoms per unit cell. So basically it's a non-primitive unit cell, the body-centered cubic. All right. So but like we saw for the face-centered cubic, it's a primitive unit cell can also be constructed out of the non-primitive unit cell. Such can also be done for a body-centered cubic unit cell. All right. So we can have, just from the lecture I will quote. So just from the you can construct a A1, which is A of x cap. So this convention is like this. So along this direction you go the whole of the lattice length of the unit cell, it's A. Along A2, that means along AY cap, you go along this, so whole of it. And now along A3 you have to go half of all the directions. So along this, along this, and along this. So this is your, so if you define the lattice translational vectors like this, you can have a one primitive unit cell. And the second case where A1 is defined as A by 2 y cap plus z cap minus x cap. All right. So basically you are targeting the body centered, I mean the atoms that are at the center of the cubes, right? So this unit, this atom is the body centered of the next successive unit cell. All right, body centered unit cell. So A1 is like, this is the convention, this is x z cap, this is x cap, and this is y cap. All right. So A1 is like half of this, half of this, and half of this part. So there is minus x cap. So this is this A1, and this is A2, and this is A3. All right. So in this type, by choosing this type of lattice translational vectors, you can construct what you can imagine a primitive unit cell, and you can naturally assume that this sorry, someone wants to enter. Okay. Okay. Sorry. Okay. So I think I got disconnected midway. Was that it? So anybody please respond. Can you hear me? Yeah. So is my screen visible now? Okay. Okay. Fine. And guys, if you have any problem with it, please feel free to ask or post in the chat box, and just interrupt me and ask in between if you have any problems. So all that. And any in general, any question from the lectures. All right. So yeah. So by that prescription, by this A1, A2, and A3 choosing like this, you can have a primitive unit cell. So now the number of primitive lattices in a BCC lattice is, and these are the two unique choices that you can get, right, to get a primitive unit cell. So the correct answer would be, there are two primitive unit cells in a BCC lattice. You can construct two primitive unit cells. So 3 questions are done. So the next question is, which of the following is the correct relationship between the lattice parameters of an orthorhombic crystal system? So for orthorhombic, this you just have to, this is an informative question. So for orthorhombic, you have A not equals B not equals C, but the angles are all at right angles. They are mutually perpendicular. So that would be the right answer. All right. Uh, Anybody has a question? Mm, Okay. Okay. Fine. So the next question is, anybody wants to ask a question? Please feel free to ask. Okay. Fine then. You have to see my screen. So a face-centered cubic unit cell is not reduced as to body-centered tetragonal or BCT unit cell because. So you have to have a draw. Let's just first draw a face-centered cubic unit cell. So this is this. So this is this. You have to draw two successive, all right? So otherwise, this is not a. Okay. These are all equal. My drawing may not be exactly like this, but these are all same. Okay. So now you put the atoms, all right? So this will go here, this will go here, this will go here, here also this, 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 also this, and this. Now it also will go into the faces, right? So this is this, this is this, this is this part, this is this, this is this. So and also and this part. All right. So what you're basically going to do is that, so if this is the case, so this, let me just put up it. So okay. So basically this is a face centered, these are a face centered two successive FCC. All right. Now what you can basically construct out of it is that you can have a, you can join this and you can have a, just connect the dots at the bases, and what you can essentially have is this and this. So this has you know body centered tetragonal, all right? So this is shorter than this. So for body centered tetragonal, this is, there's the body centered the atom that sits at the center of the body centered tetragonal, and the A and B are equal and the C is different from A and B. So this is your body centered, this is your body centered, this is your body centered tetragonal. All right. So now comes the concept of symmetry and the unit cells being smallest. All right. So although the body centered tetragonal here is small, smaller than the face centered cubic unit cell, but what will strike it is that it has lower symmetry than the face centered cubic. So two criterions, right? So there are two criterions, right? One is symmetry consideration, and the second is size. All right. So for face-centered cubic, what are the symmetries you have? I'll just quote 4, 3-fold. All right, 3-fold and 6, 2-fold. All right, but for your BCT, which is the body-centered tetragonal, it's only 1 4-fold. All right, and 2 2-fold. All right, this you learn from the lecture. Uh, so the first criteria you have to take into consideration that although the FCC unit lattice cell is larger in size than the body center tetragonal, which you can construct out of 2 successive FCC unit cells, despite that the FCC has more symmetry than the BCT. So the question that was asked is that a face-centered cubic unit cell is not reduced as true body-centered tetragonal BCT unit cell because symmetry of the FCC unit cell is higher than the BCT unit cell. So that would be your correct answer. All right. So D is your correct answer. So we are done with 5 questions. All right. So that was that. The next question that is asked. The coordination number of atoms in a body-centered cubic unit cell. So coordination number, let me just define it for you. So coordination number would be number of nearest neighbors. All right. So body-centered cubic unit cell, let me just draw it. So this is this. All right. Now just put the atoms. This is here, this is here at the 8 corners. Also, there's a atom at the center. All right. So now, what you can first think that you'll apparently think that this is and this is side plane of A. All right. So first of all, you'll be wrong in if you think that this is the shortest side, but this is not. There's also an atom at the center which sits at, if this is your origin, let me just take this as the origin. All right. So this as coordinate A over 2 x cap plus y cap plus z cap, right? Because what you have to do is go this way and this way. So half of A in both the directions, and this is your coordinate axis. This is your x, this is your y, and this is your z. All right. So think that this has distance. Let us just calculate the distance of this, right? So from Pythagoras theorem, so this is first of all, this is A, this is B, this is C, this is D, and this is, right? So let us just calculate the length of BC. BC is given by root under A2 squared plus A by 2 squared. All right. So in that case, which is given by okay. So yeah. So in that case, so what we'll be doing is that all right. So this is 2a squared by 4, and this will give you A by root 2. So now you have to apply a second Pythagoras theorem, which is perpendicular root under of BC squared plus BD squared. All right. So in that case, it will give you a by 2 squared plus and your a by root 2 squared. All right. So this is a squared by 4 plus a squared by 2. This is root under 3a squared by 4. This is given by root 3a by 2, which is less than a. So in that case, you can think that this atom has the nearest neighbors. All right, not this, not this. These atoms are the nearest neighbors. So let me just recolor. So this all will have your nearest neighbors, right? So basically, the atom at the center will have 8 nearest neighbors, and by that prescription, by the definition, you have the coordination of number of atoms in a body-centered cubic unit cell is 8. So that case is 8 for the coordination number of atoms in a body-centered cubic unit cell. So the next question is, following reason or reasons. Following reason or reasons explain the absence of n-centered cubic lattice among various Brebes lattices. All right. So let me just draw at the end. So yeah. So what's the question? Following the reason explain the n-centered cubic lattice among various Brebes lattices. So let's just draw here only. So this is your simple cubic. This is another simple cubic. So yeah. So you have atoms sitting around here, here, here. So, sitting around this places, and now you're being asked about absolute n-centered cubic. All right. So n-centered cubic in that case would be given by, you have this, this. All right. So in that case, if you first of all, if you rotate the defining symmetry is symmetry is right. So you have to basically rotate around the body diagonals, right? And the body diagonals, there are 4 diagonals, right? So this one. So you can naturally see that if you rotate around these diagonals, the symmetry will not be retained. So in that case, the first reason for it not being a Brebes lattice is that it violates the symmetry requirements of a cubic lattice. All right. So the defining symmetry, that is a 4-3-fold symmetry, so it violates that symmetry requirement. So first would be a correct answer. It can be represented by a simple cubic lattice. Of course not. I'll come to that. It is not a valid space lattice. It is a valid space lattice, but what you can construct out of it is that if you join this lattices, all right. So if you join this lattices, so what you are left with is a pure simple tetragonal lattice, right? Tetragonal lattice, which is a primitive lattice, mind you, which is a primitive lattice. So it being a primitive lattice, so the end-centered cubic, simple cubic lattice will not be a valid Bravais lattice, because you can simply create a tetragonal, simple tetragonal lattice out of two successive end-centered cubic lattice. So it is not a valid Bravais lattice. So the fourth option will be your correct option. It can be represented, so can be represented by a simple tetragonal lattice. So clear? So basically these are not allowed just because of the fact that they are becoming non-primitive lattices, but you can construct a simple primitive lattice out of it. That's why you are rejecting it as a Bravais lattice, right? So it's an overlap. So which of the following rotational symmetry is or are not present in a periodic point lattice? Of course, threefold and fourfold. So 360-degree by n, so angle, the theta will give you n-fold symmetry, right? As you already learned in the lecture. But if you so basically this threefold and the fourfold, these symmetries have to encompass the entire space, right? So if you construct space out of a pentagon, like fivefold symmetry, like this, and if you construct this, that's all right. So yeah, see, you can't accommodate a pentagon in this regime, right? In this region, it will always be vacant. So if you have a blank space and you want to fill it up with a pentagon, you'll not be able to do it. That's why a fivefold symmetry is not present in a periodic or point lattice. The catch is that whatever fold symmetry it is, it's a threefold or a fourfold, it has to encompass or cover the entire lattice space. But for fivefold and similarly for ninefold symmetry, it will not be able to cover the entire space. So the correct answer would be your fivefold and your ninefold symmetries are not allowed. Alright, so it's pretty simple. And among the 14 Bravais lattices, how many of them contain two lattice points? So let's just go to the diagram that was used in the lecture itself. Yes. So this is cubic, A equals B equals C, alpha equals beta equals gamma is equals to 90-degree. This is tetragonal. So for simple cubic, you have simple cubic, body-centered cubic, and face-centered cubic. For tetragonal, you have simple tetragonal and a body-centered tetragonal. All right. And for orthorhombic, where all the sides are unequal but they are mutually perpendicular to each other, in that case, you have all the variations like simple cubic, simple orthorhombic, body-centered orthorhombic, base-centered orthorhombic, and your face-centered orthorhombic. And proceeding on to rhombohedral, you have a simple rhombohedral. For hexagonal also, you have a simple hexagonal. For monoclinic, you have a simple monoclinic and a base-centered monoclinic, right? And triclinic, you have only a simple triclinic. Now, the question that was asked that among these 14 Bravais lattices, how many of them have two atoms, right? So let's just check the question. Yes, among the 14, how many of them contain two lattice points? So if you remember that for body centered, so all the corner atoms are for you, they are shared by 8 other unit cells, all right? So effective contribution to them would be 1 by 8 times 8. Effective contribution to them would be, so effective contribution to them would be 1 by 8 times 8 equals 1. So now for only the body centered variant, you will have an additional atom at the center of the unit cell. So plus 1 would give you 2. So for body centered, effective number of atoms are 2. So let us just count the body centered variations. So for body centered, this is 1, Body centered tetragonal, this is 1. Body centered orthorhombic is also 1. Let's say we have 3 till now. Now, for base centered orthorhombic, these atoms are shared between 2 unit cells, right? So half into 2 will also give you 1. So in addition to one body centered, we'll have also a base centered orthorhombic. So 1, this is 2, this is 3, and this is 4, and also a base centered monoclinic, right? So in total you'll have 5 such Bravais lattices where there are 2 number of atoms. So the answer to this would be that there are 5 such Bravais lattices. All right, there are 5 such Bravais lattices which will contain 2 lattice points or atoms or the motifs. This is also one informative question, that defining symmetry of cubic crystal system is your 4-3-fold rotation axis. It can have 3-4-fold and also 6-2-fold symmetry, but the defining symmetry is your 4-3-fold rotation axis. If it's not present, then despite it looking like a cube, it will not be a cubic system. All right. Now there's a representative question. So a figure is given, which of the following symmetry elements are present in the lattice shown below. So this is a simple cubic lattice. All right. So but the atoms you have here is a rhombus, or you can say diamond shape. All right. So for simple cubic, for a plain square lattice, you'll have this as the fourfold symmetry, right? So right, so if you rotate along this axis by 90 degrees in succession of 90 degrees, you'll see that there will be no change. All right, so these are also symmetric, right? These motifs or atoms, whatever you call it, these are also symmetric. So one rotation from here to here will put like this, just it will be replaced by this only. So it will have a fourfold symmetry if you rotate along the center of this square lattice, right? And also, as also seen earlier, these points will have twofold symmetry. Of course, these points will also have twofold symmetry, but the maximum symmetry you can have is a fourfold symmetry. All right. So if you rotate along these points, this will go from this. So this will go from this. This point will go from this, and this point will go from this to this. So there will be no change whatsoever if you just rotate along these points. All right. So now the two allowable symmetry rotations would be, your one is a fourfold rotation and the other is a twofold rotation. Let me just check in between their question. Yeah, so no question. I hope you're getting it. So feel free please to ask questions in between. All right. So the 11th question is solved. A set of identical crystallographic planes in a crystal system is denoted by, and this is quite straightforward. This is very informative. So this is how you define a set of crystallographic planes. So consider if you have a 100 plane. So if a 100 Miller indices plane. Now, if you have 200, all right. So these all fall under the same family of lattice planes. So in that case, you have 100 family. All right. 1 minus 1 family, that will also be allowed. So family of lattice planes, they have symmetry. If you also consider symmetry, 1 bar will also be included. I mean the negative of the x-axis. So that will also be in the same family of lattice planes. So the convention to define it is to write it in curly brackets. All right. So set of identical crystallographic planes in a crystal system is denoted by H-scale curly bracket. right? So now you are given a problem to work out. So if the intercepts of a plane on the x, y, and z axis are 3a, so along x it's 3a, along y it's 3b, and along z it's 2c. So to find out the Miller indices, you have to find out the intercepts first. So intercepts, fractional, of course, intercepts. So 3a by a, 3b by b, and 2c by c. The next step would be to calculate the reciprocal, right? So the reciprocal of this would be 1 by 3, 1 by 3, and half. Now you have to convert it into the smallest number of integers because HKL have to be integers. So you have to multiply by the lowest integer possible so that the converted number is a integer, right? So what you can do is you can multiply with 6, right? So times 6 times 6 times 6 will give you twice indices as twice, and this is thrice. So the correct answer is your HKL would be so your HKL would be your 2 to 3 set of planes. Alright. So the correct answer is your 2 to 3 set of planes. And let's go to the next question. The angle between 102 and 111 direction in a cubic lattice. Alright. So the formula that you have understood is cos theta equals h1 h2 plus k1 k2 plus l1 l2 divided by 2 set of planes, right? So this is your h1 squared plus k1 squared plus l1 squared times h2 squared plus k2 squared plus l2 squared. All right. So here h1 k1 l1 is your 102 and h2 k2 l2 is your 111. All right. So now what you get is cos theta is equals cos inverse. You have h1 times h1 1 times 1 plus 1 times 0 plus 2 times 1, right? Divided by 1 squared plus 0 squared plus 2 squared times sum 1 squared plus 1 squared. So this is basically cos inverse 3 over root. This is your 5 and this is your 3. So cos inverse 3 under root 15, and this gives you your 39.2 degrees, right? So correct answer is 39.2 degrees. If you can calculate this, just put your calculator into practice and this will give you 39.2 degrees. So this is a simple exercise, just a warm-up exercise. And yeah, the interplanar spacing in angstrom between the 110 planes of a cubic lattice with lattice parameter. Of course, we have oversimplified it. We have only learned about the cubic system. So these are all formulas where you apply it for cubic system only. Okay. Okay. So now, let me just check, was it recording or not? Yeah. So the interplanar spacing in angstrom between the 110 planes of a cubic lattice with lattice parameter 3.5 angstrom. So the formula is that, the general formula is that h squared by a squared plus k squared by b squared plus l squared by c squared. All right, so here HKL is your 110, and here asked about a cubic lattice, right? So A equals B equals C, which is given as 3.5 angstrom, right? So this is 1 squared plus 1 squared plus 0 squared over some A squared minus R, and this is A by root 2, right? So A by this equals 3.5 angstrom by root 2, which will give you a value of 2.47. So this was also very simple. So this will give you a value of 2.47. Alright, so we are done with the problems that were given in week 2. Hope I covered all of it. Yeah. So now students, it's for you to ask questions. If you have questions, if you find any difficulty at any place, please ask, or if you do not want to unmute yourself, please post your questions in the chat box itself. So I'll wait for your questions. If you have any problems that you of course you can ask from the lectures also, if you haven't understood any concept that were taught in the lecture, so you can always ask. Just wait. So yeah, please. Hello. Please go on. Uh, can you repeat your question? I didn't get. Yeah. I don't get you. Sorry, I don't get you. Can you just type your question? Question number 11, right? Right. Question number 11, right? Yes. Please. Yes. Yeah. Which of the followings? Huh. Huh. Hmm. Huh. Hmm. Yeah. Please go on. Please go on. I'm listening to you. Please go on. Okay. In that case, you have to think about how these atoms are given, right? So for hexagonal, so first of all, you have to think about the atoms or the motifs, right? So even if it's not there, in none of the atoms are there, for hexagon you can have this six-fold symmetry, right? So you can always rotate it by 6 directions, and only along the one direction, that is the c axis or the z axis, right? And if these are present, so it will still have a six-fold rotation, right? Because these are symmetric, na? these atoms which are there at the corners, which will be there as per your problem, which is for the hexagon, which will be there at the corners. It can also sustain a six-fold rotation because the atoms are symmetric, right? All right. Right. So had there been a non-symmetric, right? Let's say like a molecule, right? So in that case, if it's not symmetric, then we have to think about that how many symmetry you will have. So it all depends on the motive. In spite of having the bare symmetry of the lattice, you have to think about the atoms and the motives, right? Okay. I see a question in the chat box. Is the final exam will be a written exam or it's MCQ type? Unfortunately, I don't have this information with me currently, but I can always ask the administrator. In that case, unfortunately, I don't have the answer, right? So, pardon, I don't know currently. Yeah. So, any student has any problem? Any questions? Any general questions? Uh, yeah, yeah. Thank you. Thank you. Thank you. And, yeah, yeah. And if you have any question, like if you can figure out currently that you do not have the question, but you go back and have the find a question from this lecture, you can always ask in the coming lectures also. All right. So yeah, yeah. It's my pleasure to teach you all. So I don't see any further questions. So shall I wrap up? If it's okay with everybody, I think. Okay. Okay. So yeah. So see you in coming Friday, next Friday with the week 3 lecture. It's already uploaded. So go over it, understand it properly. And if you find any problem, I'll be there in the next problem solving session. So yeah. Good evening, everybody. Have a nice day. Stop streaming.